So do you remember what we did last time in chapter 12 for a string, standing waves on a string? You remember that? So this was the simplest waveform. Yeah, I will post it. So I was waiting till I end it. Till the end of the course. So okay, I will put the quiz averages today. So this was the simplest waveform, and we call this the fundamental waveform. And the next one was like this, if you kind of remember. And the important point in that section was the two ends. I said what determines this waveform is the two ends. Those are our boundaries. So in a tight bound string, the two ends had less freedom, right? So that is why those two ends were nodes. These were nodes. And the simplest waveform we were able to get with two ends as nodes was this. And the second one was this. And we kept on doing this, and we got the equation for frequency. I think it was something like this. N over 2 V L or something. So something like this. And N was able to get values 1, 2, 3, 4, 5, 6, 7, 8. So we did this part last week. Sorry, not last week, on Monday. So before going to the new two types of standing waves, I'm going to draw this diagram for your reference. So this is a lambda, right? This is one wavelength. And if we think in terms of standing waves, two loops make one lambda. You remember that? Yes, two loops make one lambda. Okay, so with that part in mind, let's see what we are going to do today. So I'm going to erase this part, which we did last time. And in this lesson, since chapter 12 is on sound, they are going to introduce you into sound instruments. Things like tubes, pipes, which are closed in one side. So that is one example. Is the first example. And the second example that you will learn is a tube which is open on both sides. So in the string, what was standing wave was the string, right? String was the one which was vibrating. What can you tell about this? In these standing waves, what do you think is vibrating? So I have drawn different waveforms. What do you think is vibrating? It is air. It is air. Yes, it is air that's vibrating inside the tubes. So just to kind of tell you what is happening in these tubes. Okay. So tube open at one end. That means one side is closed and the other side is open. So the closed side has higher pressure, right? It is closed and it has less freedom to move. Less freedom to move. This point has high pressure. But this point, the air can move freely because it is open. So that is our boundary condition for a tube that is open in one end. That means this end should definitely have a node and this end should definitely have a displacement antinode. Displacement means air is displacing. So This end is definitely antinode, this end is definitely node. So are you okay with the two boundaries? Okay. So in all these examples, all these harmonics, that is common. That means one end is a node and the other end is an antinode. Antinode, node. Okay. So for this boundary condition, this side node and this side antinode, this is the simplest standing wave pattern that you can draw. So this is your standing wave. So this is the simplest that you can draw, right? So this end should have the maximum freedom. That means the maximum amplitude. This end node, this end should be a node. That means you are having quarter of a wavelength, right? Or half of a loop here. Okay, now what I want you to do is, I want you to tell me this length L in terms of lambda. How many lambdas are here? So compare this diagram with my reference example here. How many lambdas are here? So you have this much, right? So your answers are almost correct. So you have to look at this part. Okay. So you have this part inside the tube, right? You have a quarter of a lambda. Yes. So we have a quarter of a lambda. So are you okay with this? So do you agree with me in this one? Because you have this part, right? You have this part inside this. Okay. So the next simplest waveform you can draw is this. You should definitely have antinode in this side, definitely node in this side. So the next one is this. So can you tell me what your L is in this example? So I got one answer. Can I have more? It is 3 lambda over 4. So are you okay with 3 lambda over 4? The reason is, can you see there are 3 of these quarter lambdas, half of loops? We have 3 half loops, right? 1, 2, 3. So 3 lambda over 4. Okay, now this one. Let's do this quickly. How many? I need more of your answers. Y'all used to give me a lot of answers before. Now, no answers. Okay, that's good. 5 lambda over 4. Why 5? Because there are 1, 2, 3, 4, 5 of the initial ones, right? Initial one was lambda over 4. You have 5 of those here. Okay. So if I write a common equation for this one, it is going to be L n lambda over 4. That is what's varying, right? In this one we had 1, this one 3, this one 5. But the thing is, n is only varying like this. It cannot have any number. It has only odd numbers. Can you see it? So 1, 3, 5. So your n will be 1, 3, 5, 7. So it can go up to any odd number. So if I write lambda, lambda will be 4L divided by n. If I write the frequency from V equals F lambda, frequency is V over lambda. The frequency I get is V 4L n. And n is 1, 3, 5 like that. So this is important because if I ask you for the first harmonic, you will just substitute 1 here, right? If I ask you for the second harmonic, what you would do? What would be your n? What is the n of second harmonic? It is 3, right? So it is different from what we did before. So first harmonic will be, let's say it is F naught. So second harmonic will be 3 times F naught. Your third harmonic will be 5 times F naught. So it is not similar to the string. In the string, it was 1, 2, 3, right? The second harmonic was 2 F naught. But in this one, if I ask you for the second harmonic, you should have 3 because the second n is 3. So do you get that part? Is it clear? So that is the part that you have to kind of remember. This is the only different example that you will see. So even other one will be also very easy, just like the string. Okay. So now let's look at the second example. Tube open at both ends. So when both ends are open, that means both ends have freedom, right? Less pressure. Less pressure. So both ends should have antinodes. So that's the condition. What is the simplest waveform that you can draw with 2 antinodes at the end? This. There's no other way to draw it, right? So let's do what we did in the previous example here. So compare your diagram, compare this, your waveform with this lambda reference diagram and tell me how many lambdas are here. L is equal to what? So you are correct. It is half of a lambda, right? So you have this part. So it is half of a lambda. Here you have half of a loop and again half of a loop. That means one full loop. One full loop is half of a lambda. Okay. The second one. So you are correct. One lambda, right? So you have two halves, which makes one loop and another loop here. Two loops make one lambda. So just to compare it with this, so I'll just write 2 over 2 to get the same pattern. So what is going to be your third one? So you are correct, 3 over 2. Why? How many loops? 1, 2, 3 loops, right? Here is a half, here is a half. One loop was half of a lambda. Okay? One loop was half of a lambda. So you have 3 of those. Okay. So if I write the common equation for this, I get n2 times lambda. And n can be anything, right? Here 1, 2, 3. Here it was 1, here it was 2, here it was 3. And if I write lambda, I get 2L over n. And if I write frequency, I will get 2L over n. And n can be 1, 2, 3, anything. So this was the exact formula equation we got for the string, right? So for the string and the open tube, the equation is the same and n varies in the normal way. That means n can be any integer. It can be 1, 2, 3, any positive integer. But if it's a closed tube means one end is closed, the other end is open. Then your equations are different. So this is the equation that you kind of have to remember and take into your mind very carefully. Because here you have a 4, that is one difference. And the other difference is n changes in only in odd numbers. So are you okay with this? Yes? Okay. So let's go to this problem. So there are two problems here. And I haven't given the velocity of sound in this one. It should be 343. Okay. So do these two quickly and tell me the answers. I will mark the answers and then I will go to the solutions. So for the first one, you should get 29. And for the second one, the answer you get is not here. So none of the above. Let's see. A long pipe is in a room is in room temperature. What is the fundamental frequency if the pipe is closed at one end? So one end fundamental means this wave pattern, right? So here your L is equal to lambda over 4. So your lambda is 4 times L. And frequency is given by velocity divided by lambda. Velocity of sound is 343. And the lambda is, we just found it, it is 4 times L. 4 times L is 3. So when you divide 343 by 12, you get 28.6, I think, hertz. So your answer is 29. Second one. So it is the same problem, but now they are asking for the second harmonic, right? So we know, since this is a pipe closed at one end, N varies like this. 7, like this. This is the first harmonic or the fundamental frequency. And the second harmonic is this. That means your second harmonic, this is not 4, this is 7. Okay, 7. Okay, 7. Is 3 times the fundamental frequency, right? So I'll mark as F0 for now. 3 times the fundamental. So 3 times fundamental is 28.6. So when you do this, you should get the answer 85.7. 85.76. That means it is not there. So your answer is D. Okay. So this is, you can see that this is different from the string, right? If it was the string, we would have just multiplied by 2. But since this is the pipe, we know it varies in odd numbers. Okay. Okay. So here you have another example which combines both types of pipes. Do it and tell me the answers. So the correct answer is A. So most of you gave the correct answer, but you all have got all 4 answers. So let's see. Consider 2 pipes of the same length. One is open and the other one is closed at one end. So there is a completely open one and there is one which is closed at one end. So we know the fundamental waveform for this one is like this. For this one, it is like this. So if I quickly write what is happening, because I'm really bad at remembering what I did in the previous slide, I'll quickly write it. So L is half of a lambda here. So frequency is velocity divided by lambda. So lambda is 2L. Here lambda is 4 times L. Therefore my frequency here is V divided by 4L. So I quickly wrote down the two frequency equation, and this is the equation for the open one. This is the frequency for the closed pipe. So what can you tell about these two? What is the bigger one? This one is bigger, right? This one is double the value of the closed one. So if I rearrange this, the closed equation, I can write it like this, right? Can I write it like this? Half times V divided by 2L, because I just wrote this 4 as 2 times 2. That is what I did. Okay. So what is this? This is the frequency of the open pipe. That means the frequency of your closed pipe is half of 300, 150 Hertz. So write the two equations and compare. So you don't really have to do any of it, even if you can see that this is double this value, then you can half it to get the answer. So the answer is A. So I got a question. The maths does not work to replace variables on the first to get the length. So we can do it like that also. So let's say you don't like what I did here. So we can do up to here. Okay. We can do up to here. And this is 300, right? So what we can do is we can find the value of V divided by L. So what is V divided by L? 600, right? If I take this 2 to other side, so I get 600. So we got the equation as for the closed one, V divided by 4L. So we have the value of V divided by L, which is 600. And this equation has a 4 in the denominator. Still you will get 150. So in this one, since they have not given the velocity, don't assume velocities and put. Okay. So if they haven't given, they haven't given. So find V of L directly and plug. If you like substitution, that method. So are you okay? Okay. Okay. Now we go to the next part, and it is like very easy. This is the easiest exam equation that you will find in this lesson. There's something called beats. So how does beats occur? When there are two very similar frequencies, very close frequencies, they will interfere and make this interference pattern. And they look like they have these amplitude envelopes. So you get a sound like increasing sound, then decreases, increases, decreases. So you hear this beat sound. Okay. And this beat frequency means this big frequency, the frequency of these envelopes. Okay. It is the frequency of these big envelopes. It is called the beat frequency. How frequent you hear these beats. And it is given by this equation. Very easy. What you do is you take the difference of the two frequencies that made this pattern. You just take the difference. So this is just a magnitude. So there are no negative frequencies, right? Magnitude. So we don't know which one is big and which one is small, but what we know is the difference is the beat frequency. And this is useful when y'all are tuning musical instruments. I have no idea what music is, but I know that it is used to tune guitars and stuff. So you will see such an example in this, the second example. So do these two and tell me the answers quickly. This I see. So yes, A and C. So two tunes have frequencies 440 and 444. So they're very close, right? So the beat frequency will be the difference between the two, just the magnitude. So what's the difference between the two? 440 and 444, it is 4, right? So you just put the number. So it is 4. Second one. So they use 550 tuning fork to tune a musical instrument. And when it is tuned, the tuner hears a beat frequency of 2 Hertz. That means the difference between the frequency of the musical instrument and the tuning fork is 2, right? That is what it means. So he has been able to come very close to this 500. But we don't know whether it is higher than 500 or smaller than 500. So it can be, sorry, not 500, 550. So it can be 548 or 552. So 552 or 548 both can give the difference 2, right? So it can be either. So your answer is C. It can be anything, 552 or 548. So okay with this one? Beat frequency. I know this is a simple one. I wanted to go through this because they sometimes combine all of this in one problem. I'm seeing problems like that. Okay. So now we are going to start the most important section of this lesson, which is called the Doppler effect. Okay. So first I'm going to draw an example. Let's say this is a loudspeaker. It is fixed on some point of a road. So it's a fixed point. Okay, so it gives sound. And there's a person, let's say that you are here just standing in the road. So you are not moving. Not moving. So the frequency that you will hear, so the loudspeaker is the one which is releasing the sound, right? So it is our source. And you are the one who is listening to this sound, right? So you are the observer. So those are the terms. Observer. So if the source or the observer are not moving, you are going to hear the same frequency or the original frequency of the source. So you're going to hear the same thing. No change. So if there is releasing F, you are going to hear F. Okay. So that is the normal scenario, right? That's the normal thing. However, if there is any relative motion between the two, relative means relative to the person, relative to the observer, if the source is moving or if you are moving, so if there's any motion between the two, the frequency that the observer is going to hear is going to be different. You will no longer hear this F. Let's say you are going to move this way. Let's say you are trying to move closer to the loudspeaker. So then the frequency that you are going to hear will be different. And that is called the Doppler effect. So when there is relative motion between the source, sound source, and the observer, there is going to be a change in frequency, or what we are going to observe is going to be different, and it is called the Doppler effect. Okay, so if you have relative motion, there is change in frequency. If not, nothing happens. Okay, so here are two examples. This is my example 1, and this is the example 2. So relative motion can happen in two ways. One is when the source, so this is the source, right? So source means which produces the sound. Okay, so here is ambulance. We know ambulance makes sound. So this ambulance is moving this way. So I'm going to call it V source, velocity of the source. So when that happens, there are two observers. So observer 1, observer 2, they are not moving. So if the source is coming closer towards an observer, the frequency the observer is going to hear increases. Okay. And if the source is going to go away from the person, away from the observer, the frequency that he is going to hear is going to decrease. So what you can think of it like, if the source is coming towards me, if the source is coming towards you, the frequency is increasing. If it's going far away, the frequency is decreasing. Okay, so that is one way of relative motion, right? Source is coming towards you or going away from you. So if I'm going to take this equation. So I said frequency changes, right? And this is how it changes. There's an equation for that. V sound. Okay. So I'm going to complete this equation. So this is the structure of the equation. This side of the equation is going to tell you what you observe. It is called the observed frequency. Okay, this is the observed frequency, and this is the original frequency. It is the frequency of the sound source. So whenever you are going to write the equation, start with this. Okay, so write this stuff. And V sound is the velocity of sound. Okay, so here, what is moving? So let's consider this guy. So for this one, frequency is going to increase, right? Because the source is coming towards him. But is he moving? No, right? So in this equation, if you see here, velocity of the observer term is on the top. It's on the numerator. But since our observer is not moving, the velocity here will be 0. So here's a plus or minus. So we don't even care whether it's plus or minus because this is 0. Okay. In this example, what is moving? So source is what's moving. So we have this term here, V source. So what is it going to do? So it should increase the frequency, right? So this here you should have a negative sign to increase this value. So when you divide V sound by a smaller value, you get a larger value here, right? Yes. So you try to divide some number by a small value, then you will get a bigger value. So you should have negative here to increase the frequency. So to symbolize that, in these equations, they usually put the negative sign on the top. That means to increase frequency, you select the top sign. To decrease the frequency, you select the bottom sign. Okay. Okay. So can we write the equation for this observer? How will it be different? V sound. There's nothing here, right? Observer is not moving, so there's a 0 here, just like this one. V sound. So source is moving, so we have this term here. So the hard part is figuring out the sign. So what should it be? Should it be positive or negative? So the frequency that this person, this observer 2 is going to hear should reduce, right? So like I said before, to decrease the frequency, you select the lower sign. See, lower sign is plus. So we select plus. Okay. To increase, select the top sign. To decrease, select the bottom sign. So are you okay with this? The observer moving part. This one and this one. So we will do more examples in the next slide. So I just want you to give a kind of idea how to use this equation. So in the first example, we looked at how how the equation will change when the source moves, right? So what if your example is like this? Here the source is stationary. So V source is 0 here. V observer is there. So observer is moving this way. So if I write the equation, so if I write the basic few things, V sound, source is not moving, that means your source term, this term should be 0, right? Source is not moving. So here you have a 0. So even if you write nothing, it's fine. What do you have here? So you have the observer term here. So observer is moving towards the source, right? Observer moving towards the source means frequency increases. So if it increases, you select the top sign. Okay. If it increases, you select the top sign. If it decreases, you select the bottom sign. Since it increases, you select the top sign. So do you get the pattern? So if the frequency increases, select the top sign. If it decreases, select the bottom sign. Okay. Okay. So that is how the frequency changes and how you would calculate it. And the other important thing is the lambda or the wavelength. So this is very important. Lambda will change only if the source moves. Can you see in this equation, you only have the source term. You don't have an observer term, right? So how do you determine whether it's a plus or a minus? That's the next thing. Look at the distance. So if the source is going away from you, lambda increases. Okay. If it is going away, lambda increases. You select the plus sign. If it is coming closer, see, can you see lambda is decreasing here? You select the minus sign. So we will look into this more in the next examples. So I just wanted to tell you that there are two examples, two equations, and this is how you will use the signs. Okay. So whenever I haven't marked any arrows in these examples, that means it is not moving. Okay, so here we cop is 0, here we cop is 0. So you get it, right? So in this set of examples, police car cop is the source. Why? It is the one who is having a sound, right? It is the one which has the siren. So cop is the sound source, and car is the observer. Okay. So now let's write these two equations for all these 6 examples. Okay. So I think if these are the only types of examples that you can ever get. So if you can write equations for these 6, that means you are done. You know everything. Okay. So let's do this carefully. So I want your attention for this. Okay. So participate. Okay. Let me use a nice color. I'm going to use red color. So I'm going to write the basic equation. You all are going to tell me what terms I have. V sound. So anything has V sound and V sound. Okay. So what do I have? V observer. What do I not have? V observer or V source? Which term I don't have? I shouldn't write. Very good. So no observer is not there, right? So we don't have to write this term. So you can keep your numerator empty, or you can just write plus or minus 0. Okay. Our source, copy is the source, right? This car is the source. So I'm going to write V cop here. That means we get that term. Now you all are going to tell me what is the sign. Is it plus or minus? So I got 2 correct answers. That means it is minus. Why is it minus? The source is coming towards the observer. That means frequency should increase, right? Frequency should increase, like I said before. Increase means you have to select the top sign. It is the negative one. Okay. So that is good. So you have the equation. So can you tell me the lambda equation? So look at the distance and determine what is happening. We cop is the source. We sound. So what should come here? Plus or minus? Lambda. So lambda is like the, you can think it in terms of the displacement. What is the distance between the two? Is it going to decrease? That means lambda is also decreasing. What should it be? Lambda decreases, that means minus. You are correct. Yeah. So lambda decreases means this is decreasing because the distance is going to be small and smaller. For a decrease, you select the lower sign, right? Bottom sign, negative. So do you kind of get the pattern? Slightly, yes. So let's do the second example, B. Example B, this one. So I'll write the basic structure. So tell me the sign, okay? So I'll just write V sound because we don't have the observer. No velocity for the observer. We have a source. So we have the cop term. So I got one answer. Can I have more? What is the sign here? So figure out what is happening to frequency. Then decide. Okay, so y'all are correct. The sign is plus. Why? The police car or the source is going away from the observer, right? That means frequency should decrease. Frequency decrease means you have to select the bottom sign. Okay. What about lambda? What should be the lambda sign? That's also positive, right? Because the distance between the two, because of what the source is doing, the distance is increasing, right? That means lambda is increasing. Increasing means the top sign, positive. Okay. Now we are good. Let's do the second example. So I will write it. You think carefully till I write the basic structure and send me the answer. So here the source is not moving, right? So you don't have this term here. This is 0 plus minus or plus 0. Car is moving, which is the observer. So now you all are going to tell me the sign. So I got one. Can I have more? So you all are correct. It is negative. Why is it negative? Because the car is going away from the source, right? So frequency should decrease. Frequency should decrease. So we are looking at the observer. To decrease, we have to select the lower sign, bottom sign. See, negative. So we are good. What about lambda here? Does the lambda change? No. Lambda doesn't change because this equation doesn't have doesn't depend on the source, right? If the it doesn't depend on the observer. So if the source is not moving, your lambda will be same as before. Okay. So till I write the next one, tell me the sign for the V car in the second one in D. I'm going to write it. You all are going to tell me. So I got one. Yeah, it is positive. That's correct. Because the car is coming towards the source, right? That means frequency should increase. If it is increasing, you should select the top sign. This one, plus. So in this one, again, lambda doesn't change because source doesn't change. Okay. Now this is the other type of example that they can give you. So all these examples, only one thing was moving, right? But here, both of them are moving. So when you are going to do this, you have to think of one at a time. So if you are going to look at the source, think that this is not moving for that moment and tell me the sign. Okay. So when you are going to look at the car or the observer, you are not going to even consider this. You are just going to think of this one's movement and tell me the sign. So independently, tell me the sign for these two. That is how you do it. Okay. Okay. So I'm going to write the equation. So you have both of them moving, right? V sound, V sound. Here the source, which is the cup, here car. So you have all the two terms. So I'm getting answers. I got two answers. Let's see. So if when we are looking at the source is moving towards the car. So when we are looking at the source, we are not even considering how this one moves. Okay, so we are just thinking in this in the cop's perspective. So according to the cop, he's trying to move towards the car, right? So this one is trying to increase the frequency. Increase the frequency means you select the top sign. So this is the sign for the cop or the source. So when you are looking for the sign for the observer, you are going to look only at the observer. So what is observer trying to do? Observer is trying to run away from the cop, right? It is going, the observer is going to decrease the frequency because it's going to go far away from the cop. Do you get that? Do you get that this car is trying to decrease it because it is moving away from the cop, right? So it is similar to this example, this one. So think independently. Think independently means don't think of both of them at the same time. Think of one at a time. So car is trying to move away from the cop. That means it is trying to decrease the frequency. To decrease the frequency, you select the lower sign, negative. So do you get it? Or do you have any questions with that? So are you okay with these signs? So when you are looking at one, just think that this one is not moving. When you are going to look at the cop, think the car is not moving and then do the sum. So lambda is also the same. So you are going to look at it only in terms of the source. That means you are only going to look at the source. What is source trying to do? Source is trying to come closer to the car, right? Cop is trying to come closer to the car. That means it is trying to decrease the distance. That means decrease the wavelength. So are you okay with this? So this is really a combination of this one, example A and example C. So you can think of them just like you did A and C. So are you okay with that? Yes? Okay. Now can you tell me what you get for this one? So I will just write the equation. You all are going to tell me. Okay. So let's see. Is it negative positive or positive positive? Oh yeah, you all are correct. Yeah, you all are correct. Okay. Yeah, you all are correct. Negative positive. Let's see. So if when we are looking at the cop is trying to run away, right? Cop is mad. So cop is running away from the cop. So it is trying to decrease the frequency. So you select the lower sign, which is positive. So you all are correct there. So in this one, the car is also trying to run away. That means it is also trying to reduce the frequency. You select the lower sign, which is negative. So negative and positive. So you are correct. What about lambda? So you only, for this, you just think about the cop. What is he trying to do? So you are correct. So cop is trying to go away from the car, right? Is going to go away from the observer. That means he's trying to increase the distance. Increase the distance means lambda is also increasing. Okay. So these are the 8 examples that you can ever kind of get. So are you okay with this 8? So practice this few times and then try to go to the lecture, go back to the lecture, and at the end of the lecture, there were like, I don't know, around 10 examples, 8 or 10 examples, where they do all of these, all the examples as a problem. So since you know this well now, I want you to take some time and do all those examples again, what they do in the lecture. Okay, so we don't have time to do this. I will do this part next week. So try to do these 3-4 problems and come for the next discussion. We will go over them very quickly next week. Okay.